Welcome to DP Tutorials by Donny Jarwa. Again, in this brief teaching module, we will highlight and emphasize on polarization density and charge density of a dielectric. We have already aware that in a capacitor, when we keep a dielectric material, that means it enhances the rate of storing charge. Now, a dielectric substance, when you keep a dielectric substance in a capacitor, that means it will get polarized. Okay? It will get polarized. When you keep a dielectric substance inside a capacitor, or when you place it in an electric field, the dielectric substance will get polarized. And when it gets polarized, all those dipole moments or corresponding atoms or domains, they will be in such a way that the positive end of the domain will be along the direction of the applied field. In this case, if one plate of the capacitor is positive and if the other plate of the capacitor is negative, the direction of the electric field lines will always be from positive to negative by convention. And from here, since there is the presence of the applied electric field, suppose if I name this electric field as E0, okay, applied electric field as E0, then all these positive end of the corresponding dipole moments, okay, all these are known as what? All these are known as our dipole moments, or we define them as the atoms, corresponding atoms or domains. Positive end will be along the direction of the applied field, and the negative end of the dipoles will be in the direction which is opposite to the applied field. Correspondingly, there will be induced dipole moment. Correspondingly, there will be induced dipole moment. The direction of the induced dipole moment will be along the direction of the domains, which means that if I take these as the domains, that means the direction of the electric field vector of the induced dipole moment will always be from positive to negative in this direction. So this will be our corresponding EI, which is our induced dipole moment. But the net electric field inside the dielectric will always be in the same direction as the direction of what? As the direction of E0, which is our applied electric field. Applied electric field. So this blue curve representing our net electric field is denoted by E. And this, which is in the direction opposite to E0, this is known as your induced dipole moment, or induced electric field, not dipole moment, induced electric field. Applied, this is our applied electric field. This sigma I is our induced, this is our induced electric field, and this E is what is known as our net electric field. Okay, net electric field. So what is the concept of dipole moment? When we take only that small dipole, suppose from here I take that small dipole, okay, this will be having positive, this will be having negative. Between these positive and negative charges, there will be small length of the dipole L, and one end of the charge will be having Q and the other end of the atom will also be having Q. So the dipole moment, suppose denoted by that P will be the charge times the dipole length. Suppose dipole length is twice L, then I will put as twice L. Okay? Dipole length will be twice L. So in this case, our induced dipole moment, denoted by some small p, okay, will be equal to the charge times the length of the dipole, which means that over here this will be Q times twice L, or in this case I can write very clearly that this will be equal to P divided by V. So what is this P? Small p is given by this Q times twice L. This is the concept. And from here, what is the volume? The volume will be the area. From here, if I have considered this, that means if I consider this what dielectric, the dielectric will be having a certain area. The area times all those electric dipoles. All the electric dipoles will be having what? Twice N. Okay. Again, if I consider this dielectric, if E is the area of the dielectric, and if I multiply it with the length of all those dipoles, all these dipoles will be having length, the dipole length of twice L, twice L, twice L. So if I multiply the area of the dielectric with the length of each dipole, so that will give you what? That will give you your volume V. So in this case, volume V will be equal to what? A times twice L. So from here, it is evident that 2L and 2L will be cut. So we get 2L and 2L will be neutralized or cancelled. So you will get P, it is equal to 1. Q divided by A. So what is this Q divided by A? This Q divided by A is what is known as what? This Q divided by A is what is known as what? Surface charge density, because okay, if I consider this dielectric substance along this end, if I consider this dielectric substance along this end, okay, and this end, okay, along that end and this end of the dielectric, it will acquire net positive charge. So the induced dipole moment over here, this will be plus sigma. Okay. Whereas at the other end, because of these minus charges, this dielectric will acquire a net negative charge. So correspondingly, this end of the dielectric will acquire minus sigma. So which means that the polarization of the dielectric itself is equal to 1 to the surface charge density, which is your sigma. Okay, which is your sigma, or we can write this as sigma I, induced surface charge density. What is sigma I? Sigma I is our induced induced surface charge density. Induced surface charge density. Then from here, if we want to find the electric field, the magnitude of the induced electric field, I want to find how much is this EI. Okay, we have indicated previously about this EI, and this EI is in this direction. That EI is in this direction. That EI is in this direction. That EI is in this direction. Okay, so how will you find the direction? How will you find the magnitude of the induced electric field inside the dielectric? So the direction of the induced electric field inside the dielectric from positive to negative, it is in this direction. That means this is the induced electric field. So from Gauss's law, it follows that our induced electric field is given by this expressions. Sigma divided by epsilon. Now the induced electric field, or the electric field inside parallel plate capacitor, is given by sigma divided by epsilon naught. Or in this case, if we are talking about induced electric field, then in this case it is not only sigma, but it is one sigma I. So from here, from this equation, we got that this polarization is equal to the surface charge density. So we can replace this sigma I by P, and this will be equal to epsilon. So we can get an equation of P, which is equal to epsilon naught times sigma I. This is a relation. Okay? This is the relation between the electric polarization P and the induced electric field E. Okay? And the induced, that means a relation between the electric polarization A, relation between, this is the relation between the electric polarization and induced electric field and induced electric field. So just go through this derivation so that you will understand the concepts, okay? The concepts concerning this discussion, and please reiterate and revise so that you will learn about them. Thank you.